Thank you. So we've been working on multicore kernel scalability for a while now. And while our problems and our solutions have changed, our approach to finding and fixing scalability problems has not. And it's roughly the same approach that everybody else uses. You pick some workload and you plot its scalability. Ideally, this is a straight line, but believe me, it never is the first time. So you profile it at, say, 40 and 80 cores, and whatever moves up the most is your top bottleneck. So you fix it, and then you plot your workload again, and you repeat this process until eventually, hopefully, maybe, you get a straight line. This is a hugely successful approach in practice because it focuses developer effort on problems that matter. For example, the Linux kernel developers absolutely swear by this approach because it focuses their vast but decentralized resources on problems that matter. And, it served us pretty well, too. On the other hand, it's not such a great approach in the long run because you never get to the point where your software is really, truly scalable. New workloads inevitably expose new bottlenecks, as does the unstoppable march towards higher core counts. But the deeper problem with the workload-driven approach is that the real bottlenecks may be in the interface design. Here's what I mean by that. Take POSIX's create as an example. Suppose several threads in the same process are calling create. Now, POSIX requires that create return the lowest available file descriptor, which means that the operating system has to serialize file descriptor allocation. You can optimize the implementation of this all you want, but there's just no way you can make this scale. But what if we could change not just the implementation, but the interface? If create could return any available file descriptor, then maybe we could make it scale. Though even then, it's kind of hard to be sure. There may be other problems we just haven't thought of yet. So while it's useful to be told that an interface cannot scale, it's far more useful to be told that an interface can scale, that there is definitely some implementation of that interface that scales. We have characterized a large class of interfaces that can scale. That class is defined by the scalable commutativity rule. Whenever interface operations commute, they can be implemented in a way that scales. Let's look back at our create example. First, does create with lowest available file descriptor commute? Well, if two threads call create and they get 3 and 4, I think it's pretty obvious which of these ran first, so no, they don't commute. Okay, but say create can return any available file descriptor. Now which of these calls happened first? Well, you can't tell, right? And nothing you do in the future can reveal which order these operations happened in, so these creates do commute. And the rule tells us that there is definitely a scalable implementation. Unlike the workload-driven approach, the scalable commutativity rule enables reasoning about scalability throughout the software design process. During interface design, it guides the design and implementation, it guides the design of interfaces that permit scalable implementations. Before any implementation exists, and well before you could imagine possibly running a workload. It gives implementers a clear implementation target. If operations commute, then they should find a scalable implementation. Finally, the rule enables systematic, workload-independent scalability testing. This can be used to guide initial implementation or to improve the scalability of existing implementations. The contributions of our work are, first of all, the scalable commutativity rule itself, as well as a formalization of the rule and a proof of its correctness. This formalization itself is based on a novel form of commutativity that is state-dependent and interface-based, which makes it applicable to real-world interfaces like POSIX that are chock full of state. Building on this formalism, we introduce an automated scalability testing tool named Commuter, which helps developers find commutative opportunities in their interfaces and take advantage of them. And finally, to show that this isn't all just theoretical navel-gazing, we built a scalable POSIX-like kernel whose design and implementation were guided by the rule and the tool. The rest of this talk is structured as follows. First, I'll talk about defining the rule, and then about applying the rule to real software. In the first half, I'll give you a definition of scalability on modern multi-core hardware, an intuition for the rule, and I'll briefly touch on formalizing the rule. In the second half, I'll talk about the tool that we've built for applying the rule to real software, and show the results of applying the tool to Linux and our operating system, SP6. So let's first understand what makes an application scale or not scale. Here are two application benchmarks from previous work running on a cache-coherent 48-core machine. One scales, one doesn't. What's the difference? Well, in this application, one single highly contended cache line deep in the bowels of a Linux VFS system wrecks the scalability of the entire application. And results like this are actually pretty common on large multicores. And this isn't even so surprising if you look at the cost of a contended cache line on today's hardware. This experiment shows the cost of n cores reading a cache line while just one core updates it. To give you a sense of scale here, a relatively complicated system called like Open takes on the order of 1,000 to 2,000 cycles. That means that a single read of a contended cache line can take 25 times as long as even a complex system call like Open. So what does scale on today's multicores? Well, it's actually pretty much what you would expect. As long as memory accesses don't conflict with each other, they scale. And conflicting simply means that one core writes a cache line that another core is also either reading or writing. For example, if two cores are both reading the same cache line, then that scales because the line can be kept in both of the core's private caches. But if one core reads a cache line that another core wrote, then the machine has to transfer the new value of that cache line to the reading core. Not only is this just expensive, but as we saw in the previous slide, it gets slower as more cores do this. So this doesn't scale. Given this, we say that two or more operations are scalable if they are conflict-free. Now, given this definition, we can understand the intuition behind the rule. If operations commute, then their results and effects are independent of order. So the interface doesn't require them to communicate. Since conflicts arise when operations communicate via shared memory, eliminating this unnecessary communication makes the operations conflict-free and therefore scalable. Now, this intuition is obviously a bit fuzzy. So in order to prove that the rule is really true, we formalized our notions of commutativity and scalability and, of course, the rule itself. Now, don't worry, I'm not going to go through this now. The details are in the paper. Though I do want to call out one high-level bit. Unlike typical definitions of commutativity, our definition is sensitive not only to operations and their arguments, but also to the state in which operations are invoked. It's actually quite natural to think about operations commuting with respect to some particular state. And in fact, there are many operations in, say, POSIX that commute in some states but not others. And this is really why we need to make this distinction. Now we can flesh out our earlier create example in more detail. So earlier we said that two calls to create from the same process don't commute, so the rule doesn't apply here. So let's instead look at calls from different processes. What about create of tempx and etcy? Well, since these are running in separate processes, the order they execute in won't affect what FDs they return, and nothing that you do in the future can reveal what order they executed in. Therefore, they commute. And therefore, they have a scalable implementation. In fact, Linux is an example of a scalable implementation of this. Okay, what about create of /x and /y? Well, they commute just like in the previous example, so they have a scalable implementation. This is actually kind of surprising, right? Because they both modify /. And in fact, if you try this on basically any operating system today, you'll find that these operations do not, in fact, scale. But because of the rule, we know there's a scalable implementation. We just have to find it. One solution is to represent each directory as a concurrent hash table in which different names map to different buckets. Okay, what about two exclusive creates of x? Now the answer depends on state. So if two processes happen to have the same working directory, then these don't commute. Because whichever goes second will fail. But if the processes happen to have different working directories, then they do commute. and have a scalable implementation. Really, this is no different from the second case, but without our state-based commutativity definition, we wouldn't have been able to distinguish these two last cases. Of course, a more careful application of the rule would reveal a ton of details that I've swept under the rug here, like, what if there's only one free inode remaining? Okay, so this can get complicated quickly. So to help developers apply the rule in practice, we've developed a tool named Commuter. Commuter helps developers systematically evaluate the scalability of their implementations. Commuter takes an interface specification, for example, something like POSIX, and an implementation of that interface, for example, something like Linux, and systematically finds cases where the implementation isn't as scalable as it could be. Unlike the traditional workload-driven approach, using Commuter doesn't require a workload, or for that matter, even a multi-core machine. Instead, Commuter starts with an interface specification in the form of a symbolic model written in Python. This is what our specification for rename looks like. Don't worry about the details here. The cool thing about this is that it's easy to write. This is basically just a straightforward implementation of rename in Python. Given this model, the first stage of Commuter uses symbolic execution to analyze all pairs of operations in the model for all possible states and all possible arguments. This analysis outputs a set of precise conditions under which each pair of operations commutes. These are the conditions for two calls to rename. The first one is sort of the obvious case. They commute if both source files exist and all names are distinct. They also commute if neither source file exists. This is a little less obvious, but makes sense in retrospect if you think about it, because both calls will simply return an error. So yeah, of course that commutes. There are also a bunch of other cases that honestly we may not have found by hand, but Commuter can easily extract from our model. In fact, the list Commuter produces is complete, and each of these conditions represents a whole class of operations that can be implemented scalably. From these conditions, the next stage of Commuter constructs concrete scalability tests, actual C code that puts the system in a specific state and invokes the two operations with specific arguments for which the operations commute. The final stage of Commuter uses these tests to determine whether a particular implementation scales. It runs the tests on the implementation and monitors every memory access to look for conflicts. Since the rule says that it's possible to make all of these test cases conflict-free, any conflict that Commuter does find represents an opportunity for the developer to improve the scalability of their implementation. Our evaluation is focused on whether the rule helps us build scalable systems. We start by showing that Commuter can find non-scalable cases even in mature systems. To do this, we took Linux 3.8, which is pretty mature, modeled 18 POSIX system calls, and used Commuter to check whether Linux scaled in all commutative cases. This map summarizes the results for each pair of system calls. Green here means that all of the test cases for that pair were conflict-free, while red means that none of them were. Of the 13,664 test cases generated by Commuter for our POSIX model, Linux is conflict-free for only 68% of these test cases. Now, admittedly, many of these are corner cases. The distribution of these test cases really has nothing to do with the distribution of calls that applications actually make, but many of these are not corner cases. In the top right corner of the triangle are operations that create and remove names from directories. This corner is bright red because it turns out in Linux that these all lock the entire containing directory, even though operations on different names generally do commute. In the middle, we have operations that take file descriptors. Turns out that in Linux, these all temporarily bump up the reference count on the file descriptor just to make sure it doesn't disappear from under the operation. But as a result, we see conflicts on these reference counts. Finally, at the bottom are address space operations, mmap, munmap, those sorts of things. These have similar problems to the first group. It turns out that they lock the entire address space regardless of what part of the address space they're working on. We have personally seen application-level scalability collapses caused by each one of these. And here they are highlighted in bright red, and we didn't have to run a single workload. Now, the rule tells us that it should be possible to make 100% of these tests conflict-free. but it doesn't tell us that it's necessarily practical to do so. So to find out how close we can get to 100% in practice, we built a new scalable operating system called SV6. SV6 is a new POSIX-like operating system. We focused in particular on the file system and virtual memory system, and we followed the commutativity rule in their design and implementation. The implementation itself mostly uses the same parallel programming techniques that you'd find in something like Linux. But as we were building SV6, we were constantly running Commuter to better understand what we were getting right and what we were getting wrong, so that we could fix things as we went. With SV6, we're able to show that nearly all commutative operations in the file system and virtual memory system can be made to scale in practice. As you can see, over 99% of the same test cases that we ran on Linux are conflict-free in SV6. The remaining 1% are mostly what we call idempotent updates. These are things like 2 L-seeks of the same file descriptor to the same offset, or 2 P-writes of the same data to the same offset of the same file, things you probably didn't want to do anyways. Are these possible to scale? Sure, the rule tells us that they are. But in these cases, we explicitly chose common case performance over absolute scalability. And the rule forced us to recognize and explicitly make this trade-off between scalability and performance. Now, the rule not only helped us build a scalable implementation of POSIX, it also helped us make changes to POSIX and SV6 to improve its scalability. We already saw one example of this. Allowing create to return any file descriptor makes it more commutative, enabling a more scalable implementation. A much more interesting example of this is fork exec. So fork is like ridiculously non-commutative. It doesn't even commute with memory writes from other threads in the same process because it's making a snapshot of the entire process. This is unfortunate because fork is often followed by exec, and exec undoes most of what fork just did. In fact, POSIX actually already has an answer to this problem. They did it for embedded systems, but we like it for scalability. It's called POSIX spawn, and it combines the steps of creating a new process and loading an image into it. So it can skip over all the stuff that makes fork so non-commutative. And in fact, POSIX spawn has a highly scalable implementation. These simple interface changes translate to huge scalability wins for applications. Here's a QMail-like multi-threaded mail server running on SV6. We originally wrote it to use the standard POSIX interfaces shown on the slide. It, needless to say, doesn't scale particularly well, despite our best efforts. And I should point out that it performs similarly on Linux too, so it's not like our implementation here just sucks. We then changed the mail server to use our improved POSIX interfaces. With these, the mail server scaled perfectly. You know, before we had the rule, getting an application to do this usually required finding and fixing dozens of scalability problems. But having already run Commuter on SV6, you know how many problems I had to fix for this workload? 1. It turned out that one of our hash tables was too small and that had slipped by Commuter. Of course, we're not the first to observe that commutative interfaces have interesting properties. For example, a lot of past work has explored the connection between commutativity and concurrency to show when it's safe to run operations concurrently. Our work complements this by showing that not only is it safe, but it can be done scalably. Like our work, the laws of order attack the connection between commutativity and multicore performance. But the laws of order show that certain non-commutative interfaces have poor performance on multicores, whereas our rule tells developers which interfaces will scale well on multicores. And finally, our definition of scalability builds on all sorts of past work, ranging from disjoint access parallelism to scalable locks to scalable reference counters. So, in conclusion, I've presented to you a new way of thinking about scalability using the scalable commutativity rule. This rule enables reasoning about scalability starting with interface design. And our tool enables developers to apply the rule to real systems and substantially improve their scalability. Thank you. You can check out more about our work at this URL, and I'd now be happy to take questions.
I'm going to talk. Okay, there we go. Finally. So when you write your specs
Mm-hmm.
in Python, how do you capture the possibility of non-determinism in the result? So you gave the example of returning any file descriptor, but I didn't see that in your rename example.
Yeah. That's an excellent question. So this is actually one place where we really take advantage of the symbolic execution. So for example, if you're allowed to return any available file descriptor, since we're writing this in sort of a symbolic world, we don't have to specify which file descriptor it is. So for example, our implementation of NEFD for create basically says, create some symbolic integer and assert that it's not some already used file descriptor and return that. And then our tool is able to see that there's all this non-determinism already allowed there and check the commutativity of that.
Thanks.
Mm-hmm.
Okay, I'm going to... Okay. I'm going to dive in with a moderator question. Do you have any intuition how much of an impact scalable implementations have on common server or desktop workloads? The mail server benchmark is an application, but arguably a somewhat syscall-heavy workload pushed to an unusually high throughput.
Unusually high throughput. Okay. So our intuition is that, yeah, it does matter. And partly this intuition is based on our previous work, right? Like we've actually run lots of real application and server benchmarks on these large multicores, and we've seen the sorts of problems that Commuter finds, right? And we've seen that those things actually affect the scalability of these applications. So we believe that at least our intuition is that this really does matter for real applications, although we would absolutely love to like run those benchmarks on our operating system.
Hi, Fitz Nolan, Yale University. The Python program that you showed, is that something that's automatically generated, or do you write that by hand? And if you write it by hand, are you worried about bugs that you might introduce in writing?
Yeah, so you write it by hand. You kind of have to write it by hand because, like at least for POSIX, POSIX is prose, right? So somehow you have to translate that into the code. We are slightly worried about bugs, and obviously you can make mistakes in this, and now you're no longer modeling your interface. One thing that we do as sort of an end-to-end check is that because the model specifies what the expected return values of these things are, we can run Commuter in a mode where when it runs the test cases on the actual implementation, it checks the return values from the implementation against the return values from the model, and will tell you that at least you screwed up something somewhere. And in fact, we have found bugs not only in our implementation, but also in our model, and actually in Linux, for that matter, just matching these things up.
Thanks.
Another question from the moderator. The insight that state matters for commutativity is the core of the red-blue consistency paper from OSDI 2012. Could you comment on the difference in applying the insight in a multicore kernel versus a distributed system?
Okay. Sorry?
Could you repeat the question? The microphone up there isn't as directed as...
The insight that state matters for commutativity is the core of the red-blue consistency paper from OSDI 2012. Could you comment on the difference in applying the insight in a multicore kernel versus a distributed system?
All right. Unfortunately, I don't remember the details of that paper, but multicore systems are a lot like distributed systems. Certainly, a lot of the constant factors and such are rather different. But yes, I think it's important to recognize that state really does matter for commutativity, because a lot of our interfaces, frankly, if you don't have state, then you won't be able to juice much of any commutativity out of them. So no. Okay.
Turn the mic on.
The Yeah, actually, I think it is. So one specific reason. Oh.
Feel free to do it in your own words.
Right. Well, now you're making me forget the question. So basically, in things like K42 and Tornado, they would switch between implementations to achieve better scalability, and he's wondering if even if you're designing the interfaces to support better to support better scalability from the beginning, if this still has a role. Is that a fair? Okay. So yeah, I think it does. And one of the reasons that I say this is that if you dive into the actual formal version of our rule, it's actually very specific what it says. It says that if the operations commute in some particular history, then there's a scalable implementation for that history. And you can sort of generalize this out from there and say, well, and you can do it for all of these histories and so forth. But one of the interesting consequences of this is that there are actually interfaces where a single implementation will not necessarily scale in all histories. I'm not sure we actually found any of those in POSIX, but they certainly exist in theory. We've got a few constructions in the paper. And for those, I think it would be exactly the right thing to do to see sort of what is the application doing over the long run, and maybe I should switch to this other implementation now.
Yeah, hello. Luis Pedrosa from the University of Southern California. How sensitive is your technique to implicit conflicts that are inside the specification that is done in Python? I'm thinking that if my mindset is that this particular system call will necessarily have conflicts, it's not scalable. I haven't thought of a way of making it scalable in the first place. I write the specification in a way that is not scalable to begin with. Maybe your tool will say, sure, it's not scalable, but that's just confirming my initial hypothesis anyway. Does it require that the specification be done in a way that does not break scalability in the first place? Or?
And by specification, you mean specifically the Python model?
Yes.
So one of the nice things about doing this symbolic analysis of the Python model is that how it actually does what it does doesn't matter. Like, it's not looking for where the conflicts are in the model. It's only looking at the external behavior of these operations. Does that make sense?
Yes.
So when it's looking at, say, two calls to rename, it's only analyzing for what arguments and what state it satisfies the definition of commutativity. It's not looking at how rename is actually working, how the rename model is actually working. It's only looking at the sort of symbolic external behavior of that operation. So like, for example, many of our implementations are, in fact, absolutely full of conflicts, but it doesn't matter to the model because all it's looking at is sort of the external behavior of these operations.
But if the operation was specified in this case to not be commutative, and no one just really thought of doing it that way, the tool will not be able to help in any way in that case.
Yeah, so it is true that that the tool doesn't really help you with the interface design of this. Yeah, so like if, one thing that it can help with a little bit is that you can look at the commutativity conditions that come out of the rule or that come out of the tool and say like, well, maybe I could make like, oh, that wasn't really what I was expecting. Maybe I can make this more commutative. Right. That's actually a little tricky to do because these are like humongous symbolic expressions that come out of the tool. But in principle, you could do that. But mostly we find that the sort of intuition behind the rule is what really helps with interface design.
Right.
And then the tool really helps with implementation.
And then could you use this? I'm so sorry, it's a very quick follow-up. If this doesn't really depend on the specification being like sensitive to that, couldn't you just analyze the original code using CLI in the Linux kernel, for example?
Yeah, so we've thought about that. One problem actually goes back to, I think it was the first question, is that an actual implementation will pin down things that you actually want to be non-deterministic in the specification. So like if you have create with any FD, then clearly the implementation of that is going to return some concrete file descriptor. It's going to pin down some policy for how you actually figure out what file descriptor to return. And we specifically want to model that non-determinism in the specification.
Thank you.
Thank you. Really quick one.
Butler Lamson, Microsoft Research. Eventual consistency needs commutativity too. Have you thought about whether these ideas might help there?
Not specifically, no. But I think it would be a good thing to think about.
Thank you.
Thank you.